So yesterday, we started in on life cycle of star, and we said that naturally follows the progression because we also introduced nuclear fusion yesterday. Whereas over the past past week or so, we had talked about fission, splitting something big, a big nucleus into something smaller, the smaller pieces. Fusion involves what? What's the gist of nuclear fusion? Chris, go ahead. Taking small atoms together and putting them together to make something with bigger atomic number, more protons. Okay? And we said that's pretty much how a star starts. Okay? Go here. Okay. So a star starts off as a nebula, and a nebula is a big cloud of gases and dust and little specks of stuff. You know, maybe some bigger specks of stuff, whatever. But what starts happening inside of that nebula? Okay. Chris, go ahead.
The gravity of like the dust and everything else starts attracting it together. Good. Until you just get one big ball.
The gravity starts pulling all this stuff together, and as gravity's pulling these things together, it speeds them up. Eventually, they get big enough, they start getting together where they start running into things, and if they're going fast enough, fusion will happen. Okay. Now, we said that a star is a balance. A star is a balance of two things. What are the two things that we're looking for in order to make a star? What has to balance out? Someone besides Chris can see answer the first two questions. Parker, go ahead.
Gravity.
So you got gravity pulling it which way? In and
outward pressure.
Outward pressure that comes from where, Parker?
The fusion.
The fusion is creating what? Heat, and so thermal expansion is causing that stuff to get bigger. So you got these two opposing forces, gravity pulling things in, the heat from the fusion causing expansion pushing out. If they balance out, we get ourselves a star. Okay? What kind of star we get is really determined by the mass of that star. Okay? And I think this is where we left off yesterday. What kind of a star we get is determined by the mass of the nebula that started it off. Okay? So, with that said, let's go here. I got the impression that you guys have seen this picture before. The HR diagram, the Hertzsprung-Russell diagram. Yeah. So, real quick, let's just review. The Hertzsprung-Russell diagram is a graph. So the graph is good for comparing things. Okay? This graph is comparing two measurements of a star. On the x-axis, we have the temperature of that star. Okay? The temperature correlates with the color of the light that it gives off. I'm assuming you guys are familiar with like Roy G. Biv, right? Okay, different colors. And that we'll learn when we talk about electromagnetic spectrum also correlates to the amount of energy that that light contains. Red is very low energy light, but blue, indigo, violet are high energy lights. Okay? So, surface temperature on the x-axis, how hot it is. On the y-axis, we have absolute brightness. Okay? It's absolute brightness, not apparent brightness. Okay? What's the brightest thing in our sky here on Earth? The sun. But that's not because it's the brightest thing out there. Right? It's because why? We're real close to it. When we talk about absolute brightness, we're talking basically about what? What will determine the absolute brightness of a star?
The amount of light created.
The amount of light, or let's go more generally, Nick, let's go the amount of energy that it gives off. Okay? So the y-axis tells you how much energy things gives off. The x-axis tells you the temperature of that star. If you notice on my HR diagram, the temperature axis is actually reversed. The real hot stuff is on the left, and the colder stuff is on the right. Why? I don't know. It's the one that was in the book that I used. So, but anyway, let's talk first about we refer to as our main sequence stars, right? This section right through the middle. Are we familiar with that term, main sequence? Okay. All right. This is where stars end up, like in their general useful lifetime. Okay. Where they end up on that main sequence is determined by how much mass they have. Really big stars, right? Stars that have a really big mass end up in the top left. Okay? You'll notice next to your HR diagram, right, there's some questions that go along with it. So stars that have really high mass end up where on this HR diagram?
Top left.
Top left. Which means, what about them? They're very hot, and they're very bright. They're very hot, and they give off a lot of energy. Okay?
Are we just talking about the main sequence?
Yep, just main sequence right now. Just main sequence right now. Okay? So that means that those stars are very hot, and they're very bright. Okay? They're very hot, which means what color generally are they? Blue, white, mostly blue. Okay? But there's a trade-off.
They don't live that.
Okay? Right? They're very hot and they're very bright because what are they doing a lot of?
Burning.
Giving off a lot of energy.
Fusion.
There we go, Nick. There's the word. They are doing a lot of fusion, right? They're taking what and turning it into what? They're taking hydrogen and turning it into helium, right? And they do it a lot. That's why they're very bright. But the trade-off being, if they're doing fusion a lot to give off a lot of energy, how long do they live?
Not all.
Not very long, right? These stars burn out relatively quickly because they convert so much hydrogen into helium, they use up that fuel real quick.
So how long is it? How long?
I mean, we're still talking about maybe 3 billion years, but in the big picture, it's not really that long.
Right, I know.
Okay?
So they should answer how long do they live?
Yes, how long do they live? Long or short?
No.
Relatively short. Okay? Miriam, go ahead. Okay, so let's talk about the next part. Okay, that's the next section. Okay. So, Miriam, stars like our sun, okay, fall somewhere in the middle, right? They're very, very average as far as temperature, size, brightness, all that stuff, okay? So, stars with masses similar to our sun form stars that aren't really bright or aren't all that bright and aren't all that hot. They're very, very average, okay? But, that's good enough for us.
So
They're in the middle, right? Yeah.
How hot are they?
They're right in the middle, right? They're not real hot, but they're not real cold, okay? How bright are they? Not real bright, but they're not dim, okay? But the trade-off to that being what? They live longer, okay? Miriam, as far as what we know, calculating the age of our sun, we think our sun is about 5 billion years old, and we think it's probably going to, what? 5 billion, okay? And we think that it's probably going to live another 5 to 7 billion, okay? The Earth has been around more like 3 billion, if I remember correctly, all right? Obviously not people, but the Earth itself.
Will people be on the Earth when the sun blows up?
Most likely not. If you look at evolution as it's happened before, most mammalian species, so most mammals, have a lifespan of 1 to 3 million years.
Oh my God.
So humans, as we know it, if evolution takes its course, humans, as we know it, we're not going to be around when the sun ultimately comes to the end. Might be like Avatar or something.
Really?
Maybe.
Or will we like a desert? Or
Will there be like those little things?
Fish, I don't know generally how long fish species last. A lot of fish species last longer. Like if you look at sharks, the design of a shark today is very similar to the design of a shark billions, or not billions, but millions of years ago. Okay?
Animals still do that?
Yeah, they'll still. No, when I say humans, right? Like Homo sapiens, right? Okay. No. The normal mammal lifetimes, if you look at how long a mammal species lives as itself, generally we're talking 1 to 3 million years. Like dolphins, okay? But now, was there something before a dolphin that was if you talk about us, right? There were primates that were on our evolutionary road, you know what I'm saying? That were before us. Homo sapiens will be gone, but will something replace us? Most likely. What will we evolve into? Probably not robots.
What do you think?
I don't know. Probably something that looks like us.
Why are we
but,
spending so much time?
You know,
I don't know.
I'm surprised that what they said is that the evolution of humans supposed to be we're supposed to get like really tall.
Yeah, I mean that's one. So.
Homo knows this.
If you got-
If the sun turns red with the earth freeze.
In like 7 billion years, but we don't care because we don't be
But-
here anyway.
That's actually we'll talk about that in just a little bit. Okay. All right. To finish this off real quick, right? On the other end of it, right? You have these stars that are relatively cool. Okay, they're not very hot, they're not very big, they're not very bright. Okay, but the trade-off being, yeah, bottom right. Okay, there's your red section. Anybody else like tremendously small things right
Yeah.
now?
Yeah.
It smells like a
It's because they're doing like food.
Yeah, they're
like,
cooking something downstairs. Miriam, go ahead.
First I thought it was some.
Could we like have a red sun and they're cool?
So, no. Okay.
So it's not
Or at least not where we are in relation to the sun, right? If we had a red star, if our sun was a red star, it would be too cold here, most likely. The big thing that works for us is that we're close enough to the sun that it keeps us warm, but we're not close enough to the sun to burn us up, right? And the big thing is that the one thing that really works for us to our advantage is that water exists as a liquid in this space where we are right here. That helps us a lot. Okay? If we're closer to the sun, what happens to all the water? It vaporizes and turns into a gas, right? If we're too far away from the sun, now it turns into ice. And things that life as we know it doesn't live that way. Right? Could other life forms live that way? Possibly, but life as we know it doesn't live that way. So if we're in the same spot but our sun is red, right? Now we don't get enough energy. It's a cold, rocky place like Mars, right? If we're too close, right? If our sun was like white or blue, now we basically turn into like Mercury, which is like a big burnt up rock, pretty much. Yeah, right now we are in the perfect location. Now, does that mean that that location doesn't exist somewhere else in the universe? No. I mean, it possibly could. When we look for other forms of life, we look in that location. We like find a star. It's like, okay, this star's kind of like our sun. Let's look that far away and see if there's any planets in that spot. You know, I mean, so those are the places that we look because that's what worked for us. You know? That's good.
But they're not hot.
Yeah, relatively speaking. I mean, they're still really hot. They're,
Yeah, I
they're
mean,
still 3,000 Kelvin,
like-
right? But relatively speaking, they're not. Laura, go ahead.
Even if there was like, or even if you could tell that there's like other planets, wouldn't we like things that would get there though?
That's the thing right now is that, even if we get a signal from something, the next closest thing to us in the universe, the next closest star is about 4 light years away. I mean, it takes light 4 years to get here. How long would it take a spaceship? Way longer than that.
What if we kept that
I mean,
like?
if we
Well,
could
if we
go
travel
close,
6 feet, it would still take 4 years to get there, so.
it would be like you go hypersleep. So we feel like we
That could be real.
For a rock.
Alright! Alright.
Why do we die? Like, I don't understand.
Alright. Let's do this.
I get so scared of that.
Right.
Oh my god! Right when she says that.
Hit people with that.
Alright. So, as long as those two competing forces remain balanced, the star remains a star. It doesn't move up or down the HR diagram. It just stays where it is, but it's still a star. And we said those two competing forces were what? Fusion pushing outward, or the heat from fusion causing it to get bigger, and then gravity pulling it in. Okay? As long as those two things remain balanced, the star is stable. Like I said, it doesn't move on the HR diagram. It just stays where it is, but it'll be stable. Okay? Top of page 5.
Just turn it.
Just for the star.
Stars will remain stable as long as the outward push from
The energy of fusion
energy of fusion. Good.
is balanced.
Keyword pull up. Yeah. All right. So gravity is just gravity. It's going to be there no matter what, as long as the mass is still there. But eventually, what's going to start happening to the fusion that the star is doing? It's going to start slowing down, right? Fusion depends on us turning hydrogen into helium. Okay? As soon as that hydrogen, well, as soon as we start running out of hydrogen, what happens to the amount of energy that the star is giving off? It's not quite as big anymore, right? So here, this gets a little bit confusing, right? But stay with me, okay? So the first thing that happens, right? Fusion slows down. It's kind of like the batteries sort of slowing down on the star, okay? It's not dead yet. It starts slowing down. And that affects that affects the balance of the star, right? If fusion slows down, what's going to be stronger? Gravity is going to be stronger. So initially, what's going to start happening? It's going to shrink, okay? So when it says, what happens to the size of the star initially when fusion begins to slow down? Okay, that's the first question that you have there. It starts to shrink because now gravity is stronger than the outward push.
Oh, because it's bringing it more
Right.
together.
But the next result of that is that if you gravity starts scrunching things down, what's going to start happening to the pressure inside of the star? It's going to go up, right? If you start taking that stuff and squishing it into a smaller space, what happens to the pressure inside of that space? It increases. So now, fusion had started slowing down, right? But if we take that stuff and scrunch it down into a smaller space, higher temperature, fusion sort of kicks back up again, right?
So it's like making hydrogen into helium.
Now, in this case, right, Allison, at this case, now, a lot of times, that fusion that starts happening from the increased pressure from gravity isn't just hydrogen into helium. Now we start taking helium and sticking it together with itself to make, like, beryllium, which is...
So is that still fusion?
It's still fusion, just a little different kind of fusion. But the biggest thing, though, being, right, if fusion sort of kicks back up again, that outward push is back. And it's back in a way that now the star actually gets bigger.
But not
Okay.
hotter.
But not necessarily hotter. Okay? And we refer to that as a red giant or a red supergiant, depending on what kind of star you were to begin with. This is going to happen, or we believe this is going to happen to our star. This is going to happen to our sun. And when it does, it's going to get so big that it's going to gobble up Mercury, Venus, Earth, and Mars. And it's going to expand that much. Basically, it's going to eat us.
Oh, so then we're gonna have to go to Mars.
Mars. No, go to Mars doesn't work for us.
I know, but what's after
Okay.
Mars again?
Good.
So it's gonna get bigger than its original form.
Right.
No, is that because like when you combine two nucleons, it's like enough for energy?
Yes. Yeah. Okay. But now that push goes out, but you're taking that energy and you're spreading it out over a bigger space, so it's not necessarily hotter, but it is giving off more energy. Okay. And that's why if you go to the HR diagram,
It'll be lower.
top right, okay, because they're cool, because originally the fusion had started slowing down, but now other fusion kicks up, so it's giving off more energy, so it's bright, but it's not really hot. You know, it's so big that it's giving off a lot of energy, right, but it's not really all that hot.
So this is for any star?
Right,
Like when
any
it
star's
starts
going to go
die?
through this, yeah, when it starts to die.
Oh.
Okay, now, what happens ultimately when he dies? Let's talk about that, okay? Okay. Once the fuel of the star runs out, so now we've run out of hydrogen, right? We've got that big crunch, then fusion started up again, right? It caused the expansion. Now we've run out of things to fuse together, right? Are there bigger things there? Yeah, there's bigger things there. But like things like helium, and if we made beryllium, right? If we want to start sticking those bigger things together, how much energy would we need? a lot more because we're trying to stick bigger positive charges together. It's just not there for us. Right? So once that fuel of fusion goes away, now we start getting to the end. Okay? Just like the mass determines what happens at the beginning, the mass also determines what happens at the end.
I'm totally wrong about this, but when could you like start combining beryllium too?
In theory,
So
yeah.
Going, like,
Yes. Hold on to that. We'll get to it in a second.
Like, doesn't that mean like the star could possibly live forever? Or would there actually be so much?
Eventually, it's too big that it just can't do it. All right. So the next thing that happens, our star, our sun, loads medium mass stars. Okay. Shows up right on the screen.
I missed it. You just have
No,
no
I
stars
said
and feelings.
Yeah, it's my question. But you don't know that.
So, I don't know that. So, stars like the size of our sun and lower, low to medium mass stars. Okay? They grow big. Okay? They become red giants. We just talked about that. Okay? What happens next? Right? So the question's underneath the first picture there on whatever page that is. I don't know. Okay. Right? How long will stars continue as giants? Until what?
Until it runs out of.
Until it runs out of stuff to fuse together, right? And still, no, not yet.
Stuff, we can do that way.
Yeah, you can use stuff. I mean, you can say until it runs out of things, until it runs out of elements to fuse together. Okay?
And now it's making like beryllium or whatever.
Maybe, yeah, maybe some things are a little bit bigger, but it's basically using up all the hydrogen that's there, right? And it's left with bigger things.
So
Like
it's not only
helium.
hydrogen when it's
Not necessarily, yeah, not necessarily only hydrogen at that point. Okay? When it's a red giant. Okay. But eventually,
Wait, when it goes to its red supergiant.
no, red's okay. Notice here. Maybe if the people behind you were talking. So, notice here there's a split in this path, right? This is the path that low mass stars take. This is the path of high mass stars. This is our sun right here. Okay? The top row of this picture, okay? Which you're seeing right there. Okay? So it's going to continue on as a giant as long as there's some things to fuse together. Once the pieces get too big and it can't fuse them together anymore, fusion stops. Right? Once fusion stops, right, what takes over? Gravity. But now gravity is acting over a lot bigger area, right? All that expansion has taken place originally. So gravity starts pulling the middle stuff together, but there's still sort of these hot gas type things that are around it, right? What is this hot gas stuff that's around the dense part? It's material. What did it used to be? It used to be the star, but now it's just kind of the leftover pieces, okay? So what does the material of the planetary nebula come? It comes from the star. It used to be part of the star. But now it's just not hot enough to do fusion anymore, so it's not a star, it's just a bunch of junk. It's left over. Okay. But there's still a real dense part at the middle. That used to be the core of the star, right? Where it was the hottest and the pressure was the greatest. Okay? It's still hot. Okay? So it's still giving off energy. But how big is it compared to how big the star used to be? So it's small. So it's hot because it used to be the core of the star, but just like we talked about before, the red giant gives off a lot of energy, not because it's hot, but because it's big. The white dwarf, which is like the core of a star that's left over, it's really hot, but is it giving off a lot of energy? Because it's real small, right? So this would show up where on the HR diagram? It would show up in the bottom left. It's on the bottom because it's not very bright, but it's on the left because it's pretty hot. Okay? Eventually, now it's not hot because it's doing fusion. It's hot because why? It used to be doing fusion, right? It's still hot because it's left over from doing fusion, right? But the gravity's pulling it down, and as gravity's pulling it down, right, what's happening to it? If it's not producing any more heat from fusion, what's eventually going to happen to that thing?
It's gonna burn out.
Well, it's going to
Stop.
cool down, right? It's going to get cooler, right? And when it gets cooler, we're left with a black dwarf. Okay? A black dwarf is just what, pretty much? Not a black hole. That's something different. It's just a dead star. It's just like, you know, a bunch of junk that's left over from the star. Okay? If we looked at the material or the elements that make up a black dwarf, what would we probably see a lot of in there?
Gas.
Beryllium, probably more what than beryllium though? Probably a lot more helium than anything. Because that's what a star does. It turns hydrogen into helium until it basically runs out of hydrogen. Okay? Here's go ahead. Consider that it's the core of what our star what our sun used to be. So really small in comparison, right?
Yeah, but like it's like small. Compared to the Earth.
Oh, it's probably still bigger than the Earth.
Oh my God.
If you consider that, if I remember correctly, I think the way how big the Earth is, don't quote me on this number, but I think if you go across the diameter of the sun, there's like 1,000 Earths that you could line up across the sun for the diameter of the sun. So it's, I mean, it's a dwarf star, but it's still a relatively large body out there in space. Okay?
So small.
Oh, it's good.
What about like a super?
That's the bottom of this here. So we're not there just yet. Okay?
Wait.
Our sun has no chance of supernova. Okay? Chris, go ahead.
Because like the gravity keeps like pumping in like
Right.
like helium. It's like,
Could you eventually do it again? It's like, in theory, yeah, except what that depends on, though, is how much mass is there, right? Because the more mass you have, the more gravity you have. The more gravity you have, then you can get things going faster, get them hotter, and eventually fuse more things together. This star didn't have enough mass to begin with to be a really big star, so the core that's left over really isn't going to have enough mass. It just sort of like, could it become a part of a star later on? Possibly, yeah, possibly it could, but who knows what that is. Okay. All right. Go ahead, Caroline.
How is the fusion at the stage like after it like starts? How's it different?
So we said that at that point it might start taking some fusion and start fusing some helium together to make some bigger things. Instead of just fusing hydrogen and helium, now it might take some of that helium there. Because remember, that kind of fusion is happening at the end of its lifetime. And at the end of its lifetime, there's more helium than hydrogen. Okay? Awesome, good.
Is there fusion during planetary?
Yeah, that's when fusion pretty much stops at that point. Once it becomes a nebula, is because fusion pretty much stops. Allison, at this point, at the red giant point, it's still pretty much a star at that point, but it's like on its last legs.
These three last steps are basically.
That's basically what happens after fusion stops. Anthony, go ahead.
What happened to the stuff floating around the nebula?
It just sort of kind of like, sort of dissipates. Because it was hot for a while, right? So that means there's still some of that expansion going on. But this would be like, just kind of stuff that's out there, Is it like rocks and things? Not exactly.
But wouldn't like gravity just want to that?
It might, yeah. So gravity from this white dwarf might start pulling it back in. But like I was kind of asked before, it won't start the lifetime of the star over again because now all of this stuff is a lot heavier than it used to be when it became a star to begin with. So the fusion really doesn't start back up again. If it did all get together, we wouldn't have fusion starting. All right, good with that? Okay, that was the boring part. So let's talk about the big stars. Really, that's better. All right, so the high mass stars, right? Pardon the pun, but your biggest stars, right? Okay, they go through a different process. So the beginning of the end is similar. Fusion slows down. Initially, that star crunches down, but then the crunching down increases the pressure and the temperature inside, and it expands, now not to a red giant, but to a red supergiant. Same idea, though, okay? But keep in mind, right, as a red supergiant, that star's coming to the end, okay? So, what happens at that point? Supergiants, okay, Caroline, and you just asked, right, the fusion is different at this point because now we can start maybe taking some heavier things together and making them into bigger things, right? Okay. In a supergiant, that same thing is happening, but now we can take even bigger stuff and make it into even more bigger stuff. Okay? the bigger when we're talking about atoms that have higher atomic numbers, atoms that have more protons.
So they're like more soft.
There are more protons than neutrons, right? They're making a bigger nucleus. Okay? In a supergiant, we find that naturally elements as high as 26 protons, that's what iron is, will get made in that star. Now, do a lot of iron atoms get made in there?
No.
Because in order to stick 26 protons together, how much energy are you going to have? A lot, because that's 26 protons that are trying to repel each other. Okay? So this is where iron gets up, things up into iron get made here. Okay? Go ahead, Mary. Not on our Earth, no, or at least not like naturally. Okay? It's already got made somewhere else, right? And it just, so the planetary nebula that was left over from another star, right, has iron in it because that got made at the end of that star. So now that iron stuff starts getting formed together and that turns into Earth, Mars, whatever.
Oh, so like it's not a renewable.
Not necessarily, I mean, technically nothing is a renewable source because it all had to start off somewhere, right? Because of the whole conservation of mass idea, you know? So it's just a matter of it just kind of gets recycled into different things. You know? When our star, when the sun gobbles up the Earth, eventually the material that was Earth is going to become part of the planetary nebula. And then that's going to go out and maybe match up with something else and turn it into an Earth somewhere else. Does that make sense? Grace, go ahead.
Okay, so like at nighttime when you see the stars.
Yep.
Are any of those stars like supergiant?
Yes, they are.
So, like,
Okay.
like if they explode into a supernova, would we be able to see it?
Eventually, yeah. But Grace, let's go back to our HR diagram. Okay. These stars here. Okay. These are stars actually that you probably know. Do you know any constellations for this? Do you know Orion? Okay. Orion has a red star in it. It's Betelgeuse. Okay, or Betelgeuse star. You can't look at I believe it's one of the shoulders of Orion. Is this star looks red? If you look, if you look at it, you kind of have to look at it and go, okay, yeah, that's definitely more red than the other ones. But it's so big that it's giving off so much energy that it's bright. Okay, not because it's hot. It's actually really pretty cold. But it's so big that it gives off so much energy that it appears very bright to us because it's giving off so much energy. Does that make sense? So yeah, you see some of those things, and you actually see some of those things because they are supergiants and they're giving off so much energy that they show up here on Earth. Okay. Now some of these blue ones, they look more whitish, bluish, but you can definitely tell they're more blue. Yeah.
Didn't what happened like a couple years ago?
Yeah, it did happen a little while ago.
You know they need the energy for the supernova to time travel.
Time travel? How far away is it? Wait, what? Oh, content.
If you look in your book, there's a picture.
Yeah, I'll have our books.
I know.